Welcome students to our video notes lesson on section 1.2 part 1. Where in this video we're going to be looking at how to find limits both graphically, which is by looking at their graphs, and then numerically, which is by looking at a table of values for a given equation. Before we get into finding these limits though, let's talk about what a limit is. So a limit is essentially the value of a function, the value that a function I should say is approaching. So what value is the y value of a function approaching as the input, which would be the x value, approaches some particular value. So this here is referring to x, right? So the x values are approaching some number, some value, and the limit, when we say find the limit, we're asking you to find what are the y values approaching? What is the function approaching as x approaches that value? So let's take a look at this example down here. In this example, we're trying to find the limit of this function, f of x, as its x value approaches 2. So right here. So we're looking along the x-axis as the x values get closer to 2, and I should indicate what the function approaches from both the left and the right. That's important. The function needs to be approaching the same value from both sides, from both the left and the right. So we look at those x values to both the left and the right of 2, and then we go up to the function, and we look at the corresponding y values that go along with those x values and ask ourselves, what are those values approaching as x approaches 2? So before we do that, I want you to think of the limit as what you would find if you were looking through an open window. And I want you to kind of keep this visual in mind every time we're talking about limits. So let me show you what I'm talking about. Okay, so here we're looking at a rough image of the graph from example A. And we are trying to find the limit of this function as x approaches 2. So the old school algebra 2 approach to this is to kind of look at a function as if it were behind a closed window, where you would just see one little sliver of the graph, just what is happening on the function exactly at the moment when x is 2. So the algebra view, what we've done up until now is we've ignored essentially what's happening on the graph to the right of 2 or to the left of 2. We kind of take all of these values out of consideration when we're just plugging a number into a function, which is considered the algebra 2 view, right? We just look what's happening on the graph when x is 2. And in this particular example, nothing's happening on the graph. There's a hole. There's no y value there. So in fact, the function doesn't exist at x equals 2. So the limit, when we're asking you to find the limit of the function, which I like to think of as the calculus view or the open window view, this is where you are looking to the left and the right of where the x approaches its value, which in this case is 2. So on this graph, we're looking at what's happening on the graph as the x values from the left and the right are approaching 2. And the calculus view, or the open window view, is where you block out what's happening on the graph exactly at 2. So you kind of imagine like a window pane is there, and it's making it somewhat irrelevant what f equals at 2, what the y value is at 2. It wants to know, are the y values both to the left and the right of x equals 2? So x is approaching 2 down here, right, from the left and the right. The question is, what are the y values wanting to come together? And if they're wanting to come together to the same point, if these two ends come together to meet, that value where they're coming together to meet, which in this case is 4, would be considered the limit of that function. And in fact, the limit still equals 4 even though the function has no value at 4. Because in the limit view, we imagine the open window with the window pane. So it doesn't matter. It's irrelevant that the function doesn't exist at 2 because the left side and the right side of 2 are wanting to come together to the same place, and the function wants to go to 4. So while the algebra 2 view may take away the window pane and allow us to see there is a giant hole in the graph at x equals 2, what it does is it also closes the window. So we can't see that even though the function doesn't exist at 2, the left side and the right side were wanting to approach 4 as x approached 2. So our open window with the window pane is what we want to use as our limit view or our calculus view for finding limits graphically. So based on that open window calculus view, then the limit of this function, f of x, as x approaches 2, as we saw, is 4. Now for part B, again, we want to continue with that sort of open window view. So we can see that right here, this time we're finding the limit as x approaches 3. And we can see that on the graph there is a vertical asymptote there at x equals 3. So the function is undefined at x equals 3. We would say this, f of 3 does not exist or is undefined. And actually we would say a similar thing over here. The function at the value of 2 does not exist. This f of 2 we could think of as the algebra view, the one that's the closed. So that's what this notation is, where you sort of block out everything else except what's happening exactly at 2. And in this function there was a hole, so that was undefined. And then in this function over here there is a vertical asymptote at 3 in this case. So f of 3 also does not exist. So then we want to think of that open window view, right? We're blocking out what happens at 3. We have our window and it's open, right? Forgive my rough drawings here, but we're looking on this function as the x values on the right hand side approach 3, so 6, 5, 4, 3.5 and so on. They're inching their way closer to 3, and then we're following their corresponding y values or output values to see what those are approaching. And on this graph I can see that they're going up without bounds. We could say that they're approaching positive infinity. So then I'd come over here to the left-hand side and see what's happening to the y values as the x values approach 3 on the left-hand side. So we're, again, approaching 3, and this time the y values are approaching what looks like is negative infinity. They're just continually dropping down without bound, so we could say they're heading toward negative infinity. So I can see that the left and the right-hand side are not wanting to come together and touch, right? So for the open window, what we're looking for is if the left-hand side and the right-hand side are coming together to meet at a common y value. And in this case, they couldn't be further apart, right? This one's going up to positive infinity. This one's going down to negative infinity. So this limit also does not exist. So let's take a look down here at an informal definition of a limit. So we've kind of looked at what a limit is, how to find it graphically, but let's kind of look at a definition for it. So we would say that f of x, which of course is your y value, as that y value becomes arbitrarily close to a single number L, so this right here is our y value, that our function outputs are getting arbitrarily close to, as x approaches c, so this here would be our x value from either side, so that's from the left or the right, then the limit of f of x as x approaches c is L. So what we talked about earlier, but kind of put into a definition form. Let me show you how we write this notation. So this limit is written this way. So we use the letters LIM. Underneath that, we indicate what x is approaching by an x, a little arrow, and then the value that the x's are approaching from either side, so left and right. And then whatever function we're finding the limit of, we just sort of write the name of that function or the equation of that function just immediately to the right of our LIM notation. And then if that limit exists, if the y values are approaching the same number from the left and right, and that number is L, then we would write that this limit is equal to that y value. So remember, this is the y value that the function outputs are getting arbitrarily close to, and this is the x value that the x's are approaching from both the left and the right. So this notation here is the open window. This is the calculus view open window. So when you see that limit notation, I want you to kind of picture the window with the window pane where we're sort of blocking out what happens on the graph at x equals c, and we sort of have this open window to the right and left of c, and we're looking to see what the y values are approaching from the left and the right, but we're not too concerned with what f of c actually equals. So this notation is in contrast to this. As you'll see in a later section, sometimes these two things are the same, right? But they don't have to be in order for the limit to exist. So this f of c, this would just be sort of the algebra view, where we don't really look at what's happening to the left and right of c. So the window is now closed, except for that one little open spot where x is c. So f of c is only what's happening on the graph at c. The limit as x approaches c of f of x is what the y values are approaching on the left and the right of x equals c. So up here, back in example A, I could also write it this way. The limit as x approaches 2 of this function is equal to 4, even though f of 2 did not exist. And then over here, we would say that the limit as x approaches 3, that was the x value that we were approaching from the left and the right, on this function does not exist because the y values were not approaching the same constant L, if you will, from the left and the right. Okay, so in our first example here, we're going to be looking at how to find the limit of this function. So see here, instead of writing f of x or g of x, they just put the equation of the function that we're trying to find the limit at as x approaches 1 from the left and the right. So we could say that our f of x in this case is this equation here. So this expression is determining our outputs or our y values, right? So we're trying to find the limit of that equation as x approaches 1. Now the first thing I want to kind of point out is if I were to just plug in 1 into this equation, I would have 1 to the third power minus 1 over 1 minus 1. I would end up with 0 divided by 0, which is an undefined value or indeterminate value. So there is no value for this function at 1. We could say that f of 1 does not exist. So now what we want to do is see, well, even though I know the function doesn't exist at 1, are the y values of this function to the left and right of the x value of 1, are those approaching or getting arbitrarily close to the same output, the same y value? So what we're going to do, we're going to kind of take advantage of technology here. We're going to plug in these x values here. So these are numbers that are getting really close to 1, but they're less than 1. So these you could say are on the left, approaching 1, so approaching 1 from the left. And then these numbers are super, super close to 1, right? 1.001, 1.01, 1.1. These numbers, if I go this way, are getting closer and closer to 1. They're kind of shrinking. They're getting smaller and smaller and closer to 1 on the right-hand side. So here's my x values. So in our table, we're picking numbers super close to x equals 1. We want to get as close to x equals 1 as possible to see what if there is any pattern in the y values, and if so, what is that pattern? So what I'm going to do here is I'm going to take advantage of this TI-84 emulator. So if you have a TI-84, you can kind of follow along. And I'm going to first go to my y equals. So if you're following along, you can go ahead and do this. If you have a Casio, the series of steps would be a little bit different, and I'd have to look them up. I don't know them off the top of my head, but I could help you with that in class. And what we're going to do is type in our equation here. So I always use this button for any kind of variable. So we're doing x to the third power, and then minus 1. I put that in parentheses to indicate that all of that is in the numerator. And then we're going to divide that by, and then I put this also in parentheses to indicate all of this is in the denominator. So I type in my equation, so that's my f of x. Okay, then what I'm going to do, I'm going to hit second window. So you can see the steps over here. It kind of keeps track of them for you. The reason I'm doing that is because I want to change. So usually, like the default is set up so that it says auto. So independent is talking about x, dependent talking about y, and auto means it automatically fills in your dependent and independent variables. But what we want to do is pick our own x's to plug in. So we're going to arrow over to ask and hit enter so that I can type in my own x's. So that was, again, second window to get there. So now I'm going to go to second table. So what I want to first do is type in, let's move this over. I'm going to go ahead and type in these x values. So I'm going to do 0.9, which is sort of close to 1, but not as close as 0.99. And I see that my output value is about 2.7. So then I'm going to get a little bit closer, right? So we're approaching getting closer to 1 on the left. And now it's at 2.97, okay? So now I'm going to get a little bit closer. And I can see I'm at 2.997. So from the looks of it, at least with this, looks like I'm approaching maybe the y value of 3. Looks like it wants to kind of approach that. But now let's take a look on the right-hand side. So I'm going to start with the one that was furthest away, the one furthest to the right of 1, so 1.1. So I can see, okay, it's a little bit bigger than 3, 3.3. So I'm going to get a little bit closer to 1.01, and I can see that it's getting much closer to 3. Now it's only 3.03, so just 0.03 greater than 3. I'll get a little bit closer, 1.001, and I can see, oh, now it's really close to 3. It's almost 3. So from the left and the right of x equals 1, the y values do seem to be approaching a common, they're getting arbitrarily close to a common number, 3. Okay, so go ahead and fill out those numbers on your table on your note guide that we got from the calculator. And from observation, from this table of values, we can safely say that the limit of this equation, x cubed minus 1 over x minus 1, the limit of that expression as x is approaching 1 from the left and the right is 3. So this is like our c value from that informal definition up here, right? So x is approaching 1, and this would be the L value. That's the y value that the function outputs are getting arbitrarily close to as x approaches 1. Okay, so in the next part of example 1, we have our second equation, which is 2 times the sine of x divided by x, and the x is approaching 0. So again, I kind of like to see, well, what's happening at x equals 0? I like to do the algebra view just to kind of see if the function even exists there. So in this case, I would be doing 2 times the sine of 0 and then divided by 0. So from your trig, hopefully you can remember that the sine of 0 is also 0. So this would just be 2 times 0 over 0, which again leaves us with a 0 over 0, something that is undefined or indeterminate. So f of 0, again, does not exist. But what we're looking for is there some y value that these output values of 2 sine x over x are getting arbitrarily close to as x approaches 0 on the left and the right. So you can kind of see these numbers here. These are negative numbers, so they're to the left of 0, but they're getting closer and closer to 0. And then these are positive numbers on the right of 0, and as you go that way, they're getting smaller and smaller, closer to 0. So we're kind of taking a look at what's the pattern with the outputs as the x values do that. Okay, so one quick comment about when you are using trig functions and along with calculus, meaning limits, derivatives, and all those things, you want to make sure that you are in radian mode. Otherwise, it won't work. So you can see that it is in radian mode. If your calculator looks like this, in degree mode, then you won't get the right values for this table. So please make sure that it's in radian mode. Okay, so we'll go back to our table. So I'm going to hit second graph to get to table, and I'm going to type in those numbers from our table. So we're going to do negative 0.1, negative 0.01, and negative 0.001. Okay, so it looks pretty clear to me that the y values are getting really close to 2. In fact, so close. Here, let me arrow over here. Let's get up here. You can see. Technically, it's 1.99999, a bunch of 9s and then some 6s and stuff. But it's so close to 2 that the calculator just rounded it right here to 2. So I'm thinking this is approaching 2. So let's go ahead and pop over to the right-hand side. So we had 0.1 for that one. Yeah, pretty close to 2. And then 0.01 and then 0.001. Yeah, pretty close to 2. Again, not exactly 2. 1.99999, so a bunch of 9s and some 6s, but basically very, 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 very close to 2. So technically f of 0 doesn't exist, but the y values as x gets super close to 0 are super close to 2. They really want to go to 2. Okay, so be sure to record those values on your table on your note guide, and then we're going to say that our limit for this function as x approaches 0 is 2. So why don't you guys at home go ahead and try these two. Fill in your table of values and see if you can find a pattern with the outputs, and then from that be able to establish the limit. Okay, so hopefully what you saw in the first one, part A, with this expression here, is that as the input values, so that would be x, as those numbers approached 2 from both the left and the right hand side, that the corresponding y values were getting closer and closer to the value of 1. So the limit in this case was 1. Then in part B, as the x values were approaching negative 4 from the left and the right, so this would be our c value, the corresponding y values were getting closer and closer to this decimal value of negative 0.125, Or if you're thinking of that in fraction form, -1/8. So that is the limit, that would be our L value, that the y values or the function is approaching as x approaches -4. And then in the very last one, we could see that the y values were getting really, really, really close to 5. So that was our limit for part C. Okay, so in example 2, we're going back to finding the limits graphically and taking a look at the graphs of these equations. So here I'm finding the limit as x approaches 0 of this function, sine x divided by x, which we can see the graph of over here. I notice that right at the x value of 0 that there's a hole in the graph. So I notice that f of 0 does not exist. And if I plugged 0 in for x into this equation, I would have the sine of 0 again, which is 0 divided by 0. And that does not exist. Okay, so, but if I look at the graph and keep in mind that open window view, the calculus view, that's what this limit is. This is saying I'm not so much concerned with what's happening at x equals 0, but rather what the values of the function are approaching as x approaches 0 from the left and the right. And from the left and the right, I can see that they're both approaching the y value of 1. So graphically, I can see that this limit would be equal to 1. Even though there is no value of the function at 0, the limit still exists because the left-hand side and the right-hand side of this function are both approaching the y value of 1. Over here in part B, I can see the same thing. Actually, this is one of those cases where the function is filled in right there. So, and the left side of the function and the right side of the function as x approaches 0 and f of 0 are all the same. And in this case, they equal 3. I can see that if I plugged 0 in for x, I would have 0 to the third power plus 3, which of course is 3. And then I can also see on the graph that the y values on the left are coming up to 3 and on the right are going down to 3. So the limit is also equal to 3. So that's what it looks like when the limit equals the value of the function. There's like no break in the function. It just continues all the way through. So let's go ahead and finish up with these U-trites together. So taking a look at part A, we have this equation of the function. It's a piecewise function. So for every x value other than 3, that's what this means, the function is determined by this equation x squared minus 4x plus 1. So that would be the left-hand side and the right-hand side as x is approaching 3, because we're looking at 3 in this case, the limit as x approaches 3. So I can see that that limit exists because the left-hand side of the function and the right-hand side of the function are both tending toward or approaching the y value of -2. Even though I see this dot down here, so I could say that f of 3 is equal to -6. I noticed that. And I noticed that these two things are not equal. But remember, the limit that we're looking for is the open window view that we saw earlier, where we're ignoring what actually happens at 3. So there's kind of like this window pane, right? And we're only looking at what are the y values doing to the left and right of x equals 3. Oh, they're approaching -2. So this is our limit. This is the open window view. This value down here at -6 would be the algebra view. The view where we close the window and all we can see is what's happening on the graph of the function at x equals 3. Okay, so that would be -6. That's this notation here. But that's not what this is asking us to find. This is asking us to find the limit, which is what are the left and the right sides of the graph approaching as x approaches 3. So this is -2. And then on this one over here, we have a function with a hole right at x equals 1, right? And that's the c value that our x is approaching. So you could say that f of 1 does not exist, right? We have this hole right there, it doesn't exist. But I can see that the y values to the left and right of x equals 1 are wanting to approach 2. So this limit does exist and equals 2. So that concludes our video on finding limits graphically and numerically. I'll see you in class.